So are you able to see my screen, students?
Yes, sir.
Yes, sir.
Okay. So in the previous class, I was talking about RLC layer, where we were talking about three modes: an acknowledgement mode, and the transparent mode, where we'll be using the transparent mode when you don't have anything to do at the RLC layer. So that way, all the signaling messages coming from RRC, they bypass PDCP layer and also they bypass RLC layer. They end up going to the MAC layer. That way, the MAC layer directly talks with the RRC layer, bypassing these two things, okay, for the control signaling point of view. So what we look at today is we'll continue the discussion on other two modes, that is UM mode and AM mode. I think you have seen in the previous class why the UM mode is useful. So it is meant for sending the data without waiting for any acknowledgement. That means there is no ARQ in terms of retransmitting the packet. So this is useful in the case of real-time applications like voice over IP and video streaming, or RLC, which cannot afford any delay in the transmission of the data. If at all you want any reliable delivery, that can be configured at the MAC layer by using something called hybrid ARQ. And also you can do like lower modulation and coding scheme, which inherently improve the probability of the packet getting successfully delivered. So these are all various tricks. Even though at the RLC layer you are not doing any reliable data delivery, by doing retransmissions by employing some kind of ARQ mechanism. So I was talking about RLC does framing, or kind of also called as segmentation, especially when the packet size is bigger. That means we are getting a PDCP packet to the RLC layer, and RLC layer is keeping that in its buffer. Like so, this is the transfer buffer that you see at the RLC layer, and it keeps it and it waits for the MAC layer to decide how much can be transmitted in the upcoming scheduling interval. So depending on what the MAC layer scheduling decision is, it has to take certain number of bytes from the transmit buffer and has to create a MAC frame and send it over the air. So that is the responsibility of the RLC layer here. So here I'm talking about how we'll do the segmentation. So in general, if you look at the illustration at the bottom, so when you're sending the typical RLC SDU without any segmentation, it looks like this. And all the fields at the top that you see it RRR, they are all becomes like a reserve field when you are not doing any segmentation. And the data follows after that. But in case if you see that data that you have, that means the PDCP packet that you got, which is kept in the RLC buffer, is more than what the MAC layer can currently send it in the scheduling interval. We have to segment and send it a part of that. In that case, you will be creating multiple segments. The first segment will have this kind of format. You can see it here, where now the reserve fields will have certain meaning here. So now it has the sequence numbers. Okay. And then we are talking about this as the SI. And this is the data that is part of the first segment. And if you look at the second segment onwards, we'll have the sequence number, which let's say if it is the sequence number is 100, all the segments of a given packet will be having the same sequence number, but they have different segment offset. So at the receiver side, you can use the sequence number to figure it out that okay, whether they belong to the same SDU or not, and you can try to combine them by looking at the offset. And also we have the segment information field carries additional information. It tells what you received is the first segment, or whether it is the last segment, or whether it is the intermediate segment. That way you can kind of look at SI field along with the segment offset and the segment number to be able to reassembly at the receiver before sending it to the higher layer. So that's what happens at the RLC layer in terms of segmentation and reassembly. So that's what is happening on the right hand side, you can see. So any queries anybody having on this particular part? I kind of
Sir,
covered this part in the previous class, but yeah, if you have any queries, I can answer. Yeah.
sir, in the subsequent segments, why are we having two segment offset, sir?
No, no, it's not that two segment offset. It is not, in other words, those two, like you see, right, 8 bits, right? Segment offset is 16 bits, basically.
Okay, okay,
It's not that we have two of them,
okay,
okay?
okay, sir. Yeah.
Yeah. And I also have shown this part where I was showing an example of the scheduling algorithm has decided to send 1000 bytes in the upcoming scheduling interval. I was showing you this example where we can take 400, 400, and since you don't want to waste the rest of the thing, what we are doing is we are doing the segmentation here. We are not doing the segmentation in general. We want to send PDC packet as it is. Only for the remaining part of the Mac PDU, rather than doing the padding, we are splitting the one of the PDCP SDU, and whichever the part that can fit in, you are kind of, in this case, yeah, if it is 200, yeah, you can pack these three together to send as part of the one transport block. That's what we are doing it here. And also this is coming here. Maybe I will talk about this when I am going to discuss again about the MAC layer. It has something called distributed MAC header. As you see, each RLC packet has its own corresponding MAC header. It is called a subheader. It's not that I have, if you look at Ethernet and Wi-Fi, what we'll have is we have this header, then we have the payload, and we have the FCS. Right now, what I'm showing is we are taking multiple RLC packets and we are adding one header for each of the RLC packet that you see here. So it is a kind of a distributed header rather than having subheaders at the part of the starting of the MAC frame. In LT, it is done that way, where all the subheaders are kept at at the beginning of the MAC header. But in the 5G, they are kind of distributed. I'll come back and discuss why it is done when I'm going to talk about the MAC layer part of today's class. Let me talk about the most interesting mode at the RLC layer, that is the AM mode. So unlike the previous two, this AM mode RLC entity can be used in bidirectional mode for sending data in downlink and getting the things in uplink. And it is nothing but the UM mode with the ARQ, so that you can able to send the negative acknowledgements and get back the lost packets. That way you can kind of provide reliable delivery, similar to the way you get reliable data delivery in the case of TCP. So that way AM mode is kind of resembles what TCP does. Only the difference being TCP works at end to end, whereas here we are talking about layer 2. That means we are talking about one sender and receiver, in this case over the wireless medium. And if you look at interestingly what happens in the case of AM mode is it can be used to carry traffic in a reliable fashion, like use specific RRC messages, which are sent over RLC TM mode and TCP traffic on dedicated traffic channel. So I was mentioning in the previous class or even the beginning of today's class, RRC messages are sent in transparent mode by bypassing RLC layer. But that is the case most of the time. But there are some RRC messages that you want to send in a reliable way. For that particular case, what you do is you'll be sending those RRC messages using the AM mode of the RLC. And also when you're talking about the applications which require QoS with low loss rate, like TCP applications, then also you can be using the AM mode. So whenever you need reliable data delivery, you create one RLC entity in AM mode. In this case, what happens is the physical layer is typically configured with packet error rate in the order of 10%. Physical layer, we have this one at the order of 10%. In other words, the hybrid IRQ that is running at the MAC, that will ensure that the logical link that is created at the physical layer between sender and receiver doesn't have the loss rate more than 10%. But even though it is 10%, which is kind of not acceptable in the case of TCP, what we do is at the RLC layer, we'll be using the ARQ mechanism so that even though it is 10%, because we are doing the A mode at the RLC layer, it will be in the order of 10 to the power of -6. So that way, let the physical layer try its best with the PR configuration as 10%. But with the ARQ at the RLC layer, we can able to mask most of the packet error rates and able to achieve the loss rate in the order of 10 to the power of -6 or something, which is what you expect for a TCP kind of traffic. So look at what is happening when you take the A mode with the illustration. Again, similar to the UM mode, you are taking the PDC packets and adding a header and keeping this in a transmit buffer. And if needed, yes, you also may be doing the segmentation. If you are doing the segmentation, you have to modify the header, account for first segment, last segment, or intermediate segment. And then you add the header. So here you are generating the header, whereas here you are finally adding the header. Okay. So this is like a RLC PDU. So a copy of the RLC PDU is kept in the retransmit buffer because in this case we are talking about ARQ in the case of packet loss. And then you are sending to the MAC layer. So at the receiver again, when the packet receive, yeah, you keep it in the receive buffer. So you have to keep it in the receive buffer because when you have the segments and you have to wait till all the segments of a given packet are coming. So that's the reason why we need the receive buffer, even though we are not actually doing any in-sequence delivery at the RLC layer. If you recall, I was saying that in-sequence delivery is something that is guaranteed only by the PDCP layer. It is configurable. RLC is not doing any longer any reordering of or reliable in-sequence delivery, in other words. But still we need receive buffer because we are doing the segmentation. And at the center side, yes, we need retransmit buffer because again we are doing ARQ mechanism. Then you remove the header, and once you have all the segments of a given packet come together, you do the reassembly. But let's assume that you send a packet which doesn't have any segments. In that case, then your packet need not be kept in the receive buffer. You simply do the remove header and send it to the PDCP layer. In that case, SDU reassembly is nothing but simply removing the header and sending to the PDCP layer. So it has a slightly different frame structure in terms of segmentation point of view, unlike what you have seen in the case of UM mode. Here also we are using sliding window protocol. That's what I was mentioning earlier. We are using sliding window. I will show with an example how we will be using the sliding window protocol at both the sender side and receiver side. And also it has something called very interesting pooling concept. So if you recall in the case of stop and wait or even the go back in or any kind of sliding window protocol, you send the packet and the receiver will be sending acknowledgement. For each packet there is an acknowledgement, that's or positive acknowledgement if it is received. Otherwise, if the CRC fails, you can also configure the system with the negative acknowledgements. But what you see here is it is something quite different. Even though it is possible for the receiver to send these positive or negative acknowledgements to the sender, the way it is done in 5G is we don't send these acknowledgements just like that to reduce the signaling overhead. Rather than that, what is done is we do this pooling, where the sending entity seeks the packet reception status. So periodically, the sender can ask the receiver, tell me how many you have received and how many you have not successfully received. So depending on this status report coming from the receiver, sender can understand which packet require retransmissions. That way, yes, it is sliding window, but the acknowledgements don't come just like that in this case. So for that, we use something called status report PDUs. So we have two kinds of PDUs. One is the data PDUs, which carries the user data. Other one is the status PDUs, which contain the acknowledgements or the negative acknowledgements in a response to a polling request sent from the transmitting entity. Yes, RLC does retransmissions, but it doesn't do any of kind of reordering. And resegmentation can also happen. When you say resegmentation, yes, first you send one packet as segment 1, segment 2, and segment 3, but it so happen that uh, some of these segments are lost. In that case, sender has to retransmit. So next time, this may try to send it as 4 segments. So can somebody think of why next time it may happen to have 4 segments while earlier it was sent in 3 segments?
Maybe because the the time resource is not enough to carry big segment sizes. That's why we are cutting it down to smaller segments.
So what is not sufficient? Suranjan, tell me again.
The radio resource, like in case of TDD, the time, or in case of FDD, the bandwidth.
Okay. Yeah, at a high level, what you said is okay. See, whenever you try to send something and if it is not successful, next time you want to be more cautious, right?
Right.
So what is cautiousness thing that you do here? The MCS.
Yes.
Yes.
So next time you may be sending with lower MCS, like maybe earlier maybe trying with let's say 32 QAM. Now you reduce to just QAM. In that case, you may not be able to fit everything in few segments because the radio resources which are assigned cannot accommodate entire payload in 3 segments. It may end up into 4 or 5 segments. That's the reason why I'm writing here resegmentation to adapt to the channel conditions. So because at the end of the day, you want to make sure that data is delivered even though it took certain number of retransmissions. Okay, so that is the point.
Sir,
And sir, yeah, continue.
yeah. Sir, here this polling is happening between the UE and the G node B, right, sir?
Yes, yes.
Okay. Yeah.
Sir, here we are using status PDU, so it is a different PDU session is created between the UE and the UPF.
No, 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 no. Okay, so wait. See, don't confuse between PDU session with the status PDU. PDU session is something that is established when a handset is connected to the network,
Yes, yes.
right? When I'm talking about status PDUs, at the RLC layer, I'm talking about two kind of PDUs. One is the data PDUs. In other words, data RLC PDUs. Other one is the status RLC PDUs.
Okay, okay.
Yeah, these are nothing to do with PDU session establishment. Okay.
Okay.
Okay. And also look at the segmentation part. We have slightly different structure here. As I was mentioning, if we have this DC field, it tells whether what is being carried is the data or it is a kind of a control information. And there's also a polling bit. So as you see it here, when this polling bit is set, it basically means that you are expecting the receiver to send you the status report. So that is a kind of thing. And look at here, we have again segment information here, the sequence number here. The sequence number is kept, like as you see here, it doesn't mean there are two sequence number. Together they form one sequence number. This is in the case of first segment or in the case of complete segment. Whereas the subsequent segments will have this kind of structure. Again, the segment offset, if you are doing the segmentation. Because the first one anyway will have the segment offset as 0. You need not to send that for the first segment. And these two together form the sequence number, which is the same as what you have inside the first segment. So slightly different. The reason why we need to have a different thing is, unlike in the case of UM mode, in the case of AM mode, we are expecting status reports from the receiver by doing the polling. So to accommodate this polling request and other thing, we use a slightly different structure for AM mode. Okay, I think in summary, this slide is saying what AM mode does. There is no reordering, and because we are not doing reordering, it is possible to have these out of sequence reception. Why we are doing here is we have multiple. Wait. Okay. This is not at the RLC layer, but this point is specific to the MAC layer. I will talk about what MAC layer does. So MAC layer does again hybrid ARQ, but the hybrid ARQ that you have at the MAC layer is based on stop and wait. And at the RLC layer, we are doing this sliding window protocol based retransmission mechanism. So because of the scale at which the MAC layer and RLC layer is working, it is possible that certain packets may be delivered by the MAC layer out of sequence. For that reason, we will be using RLC sequence number to detect it. And we also have something called T reassembly timer. This is basically used to detect losses in a hybrid ARQ process and to limit maximum time for missing PDUs. Only will be using one RLC T reassembly timer that is used on the first received out of order sequence PDU. And all other PDUs, like if you are receiving, set it on N+1, all other PDUs are forwarded directly to the PDCP layer because we are not doing any retransmissions. Or no, we are not doing any reordering or in-sequence delivery here. Only when you are expiring this kind of timer, you'll be sending the status report to the transmitting entity for getting them retransmitted. So I'll explain what I'm telling here with an example, then you will understand better. Let's look at this example. Okay, so let's look at what is happening at t different time steps. T equal to 0, t equal to 1, t equal to 2. So at the sender side and at the receiver side, it is sliding window protocol. Okay. So if you look at what is window size here, the window size.
5 or 6, I think.
Yeah, window size is equal to 6. So what is the meaning of window size of 6?
Well, we'll be like having 6 things until acknowledgement comes, and in this case, polling will be done to acknowledge.
Yeah. So the window size kind of signifies how many packets the sender can, or in this case, transmitter can transmit without waiting for acknowledgements. After transmitting 6, still if there are no acknowledgement from the receiver, it has to block, similar to stop and wait, rather than doing blocking after transmission of each packet. That way, when you have this larger channel bandwidth, we can able to send multiple packets which can be in the air rather than wasting the channel resources. So let's assume that somehow they agreed upon to have the window size of 6. So this illustration is showing that the N-1 and N-2 packets are transmitted successfully, received successfully, and acknowledged successfully. That's the reason why you see the window is not pointing to N-1 and N-2 packets. After that, we have this N, packet N at the, I'm talking about this part, okay. I hope you are able to see this one. I'm talking about this. The sender has transmitted N, but it is not yet got the acknowledgement. That's the reason why the color is different. So here the red color denotes the transmitter has sent N, but it is yet to get acknowledgement from receiver. And if you look at the receiver window, it is pointing to 6 empty slot. Basically, it can receive 6 packets as long as they fall within this particular window, like in this case n plus 1, n plus 2, so on till n plus 6. That is the meaning of the receiver window. And look at what is happening at the center side. N plus 1, n plus 2, n plus 3, and n plus 4. So this is the kind of case where we don't have we have not even transmitted these n plus 1, n plus 2, n plus 3, and n plus 4. So they're yet to get transmitted. And we don't have any payload even to send, even though we have the window size. That is the kind of situation that we have at sender and receiver at t equal to 0. I hope this point is clear to all of you. There are two packets which are transmitted and acknowledged. Packet n is the one that is transmitted but yet to acknowledge. N plus 1 to n plus 1, n plus 1 to n plus 4 are the packets which are there at the sender side, which is yet to transmit. And n plus 5 packet is yet to even arrive at the sender. So that is the situation at the sender. And at the receiver, it has a window of 6 which it can receive as long as the packets are having sequence numbers n plus 1 to n plus 6. Okay, let's look at what is happening at t equal to t plus 1. This is the case. Sender has transmitted n plus 1 and n plus 2. And unfortunately, n plus 1 is lost. So this one is lost. And this one is successfully received. So that is what is being shown here. Because the receiver has received n plus 2 and it has not received n plus 1. Basically, by looking at the sequence number, receiver can come to know that, okay, previously I received n, now I am receiving n plus 2, means n plus 1 is lost, or something is wrong in receiving n plus 1. For that, what receiver does is it sets a timer called a T reassembly timer. Like it is in the order of a few microseconds to few milliseconds. So it sets this timer and sees whether the underlying hybrid hierarchy at the MAC layer. So the way it happens is the RLC layer has sent this n plus 1 to the MAC layer. So what MAC layer does is it establishes a stop and wait protocol and starts sending this packet n plus 1. It will send and it tries to get the acknowledgement. If it is not getting acknowledgement, it will retransmit. Like that, it can keep on trying multiple number of times for each of that at the MAC layer. Again, don't confuse here. The illustration is about what is happening at the RLC layer. But what I'm trying to say that when n plus 1 is transmitted by the RLC layer, what could be done at what might have been happening at the MAC layer. In this case, it so happened that for n plus 1 and n plus 2, the MAC layer has established two hybrid hierarchy processes. Basically, two stop and wait protocols or two stop and wait processes are used to send packet n plus 1 and packet n plus 2. It so happened that these two stop and wait processes are working in asynchronous mode, and n plus 1 got delayed or it has completely lost even after retrying multiple times using the stop and wait protocol running at the MAC layer. But n plus 2 has been successfully received. So that is the kind of situation where you see this kind of situation at the receiver, where it has received n plus 2, but this is not received. In this case, it is setting a timer. And look at what is happening at a time t equal to 2. So this is a case where without a sender as retransmitting n plus 1. So look at here, even RLC can retransmit. N plus 1. But this is an example where even before RLC timer is expiring and RLC sender has to retransmit n plus 1, the stop and wait process that is running between sender and receiver for the packet n plus 1 has successfully delivered n plus 1 packet to the receiver. It is like the layer below itself has did its magic and kind of able to deliver even though it is taking certain amount of the time. In this case, the receiver will update the window and it can start acknowledging if at all it is configured in autonomous mode, or it will wait till the sender asks it to send a status report about what packet it has received. Is this clear what I'm saying? So I will talk about a bit more complicated case in the following illustration. So this is a little bit a straightforward case. Uh, any queries or any clarification needed on this slide?
Sir, here instead of acknowledgement, we use the polling, right? So polling is always initiated by the sender, right, sir?
Right, right.
So at a particular time interval, it will keep on checking what all packets the receiver have received by with this polling. Is it so?
Yeah, basically it will ask periodically or depend whenever it is sending the last packet, it will ask the receiver that, okay, I'm done with sending all my packets. Could you please update me whether you received all of them? That is one approach. Or it can be periodically configured rather than for each packet. Maybe let's say 5, 6 packets. It will ask, okay, I already sent you 5 packets. Could you please tell me what happened to them? Something like that.
Okay, so until the sender receiver, until the receiver sends the polling status back, it will be in the red color only, or
Yeah,
it will be
exactly.
buffer.
Because you are right. Whenever you are getting the status PDU means status PDU contains the status of whether it has successfully received or not. In this case, if it so happens that it has polled, let's assume that after t equal to 2, let's call it the t equal to 3, sender has sent a poll request. As a reply to that, we get a status PDU. Then you get to know that, okay, n plus 1 and n plus 2 are delivered. So then what happens? You'll be having this window 1, 2, 3, 4, 5, 6, yeah, updated something like this, and these three also become green.
So even though the receiver have received the packet, it will still keep the window limited until it replies a poll status PDU.
Yes, yes. And one other point is you should note here is look at this example at t equal to 1.
Sir, there again, sir, why is the window 6 then? It should be 5, right? This at the receiver side, the N is in orange or red. So
Which one at t equal to 2 you are talking?
T equal to T0.
T0.
Left one, sir.
Okay, so what you are saying is the window.
On the receiver side, this N is red, right? Then the RX window should be, including N, it should be 6, right?
Oh, so it has sent n and it has already received n.
Yeah, but that red color means it is not acknowledged, or the poll status PDU have not been sent.
Yeah, that is okay. But see, basically the receiver window tells uh, what are the 6 packets that it can receive, right? So this is an example where, see, it is a kind of a transient or transit situation where the receiver received n, it is a kind of preparing the acknowledgement or it is ready to accept another set of 6 packets. So in that case, it will have this kind of situation. But what you gain by keeping the window size as 5 rather than 6 in this case at t equal to 0.
Yes, sir. I mean, ideally, because the receiver have received, it can actually keep the window as 6. But in rest of the illustration, the receive window. Oh, okay, this is because the packet was lost. Okay, sir. Yeah.
It needs to reassemble the packets, right, sir? So before receiving everything, how is it shifting the window?
Oh, no, I didn't get Madhuri. What you are trying to say?
It is like, is this like, these are like different packets, or is it, if it is segments, then
Okay. This example is no segmentation. Okay, so I'm not
okay,
complicating the thing. Okay, no segmentation here. So that will complicate it even further.
okay.
Yes, sir.
Okay, I was about to say this point. Just hold on before you
Yes,
ask
sir.
anything further. Look at this case at t equal to 1. Okay, maybe let me erase this part. Look at what happened at t equal to 1. It has received n plus 2. and this one is lost or not yet received, right? And as soon as it receives n plus 2, this is sent to PDCP layer. Even though window point of view, you see that n plus 2 is there in the window, because we are not doing any reordering. And also I am saying there's no segmentation. N plus 2 is like a standalone packet that we have received at the receiver. Immediately n plus is sent to the PDCP layer. But still you make a note that in the window, yes, n plus 1 is missing, and you set a timer and see whether before the timer expires, sender can successfully transmit n plus 1 or not. This is the example where that has successfully happening, because we are using stop and wait processing at the MAC layer. Is that okay, or any other queries?
Yes, sir. Thank you. Got it.
Okay, now I'll go to the bit more complicated case. So we are going to continue the timing. So now we go to t equal to 3. Look at what is happening at t equal to 3. I think maybe somebody can explain by looking at the illustration itself. Carefully look at the illustration and tell me what you understood by looking at window size at the sender and receiver at time t equal to 3.
Sir, so like I can try.
Yes, yes, yeah.
So in the previous case, n plus 1 was not received at the receiver, and
Received, right? Look at here at t equal to
sorry,
1.
yeah. Okay, yeah, I was looking at t equal to 1. Okay, yeah. So t
Yeah.
equal to 2 it has achieved. So okay, so then n plus 5 has come out of order. So n plus 4 and n plus 3 has not been delivered by the underlying MAC layer. So because n plus 5 was received at the receiver, then it started the T reassembly timer for that.
Yes, so that way it is setting a T reassembly timer for n plus 3. That's what happened at t equal to 3. So let's look at what happened at, you are right. So let's look at what is happening at t equal to 4. Okay, I think I have a small, okay, before I talk about that, yeah. So what could be happening? There could be two situations. One is what happened in the previous slide, where because we are using the stop and wait process at the MAC layer, n plus 3 and n plus 4, which are not yet received, might come successfully. That is one positive thing to happen. But again, I don't want to explain the same thing in this slide as well. So I want to take the worst case situation. What is the worst case situation to happen here? What is the worst thing to happen here at t equal to 4?
3 and 4 are lost.
Yeah, so yes, assume that t and 4 are lost, or they are not yet arrived before the timer expires. The timer that you have set at t equal to 3 for not receiving n plus 3 got expired at t equal to 4. Right? That is possible, isn't it? So when the timer is expiring, what the receiver will do? What do you expect the in general receiver to do? Okay, so I think, oh, there is one more thing that is happening. Okay, fine. Yeah, that is also there. Okay, so what the receiver will do when the timer expires? What do you expect it to do?
Well, if the timer should expire on the sender side, and the sender side should realize that it has not realized acknowledgement.
No,
It should,
so
that is
Ranjan, we have a timer at the receiver, not at the sender.
right. I was saying that is for the normal internet, normal IP.
Okay, okay.
But here, since we don't have that mechanism, well, when the sender sends that polling message, it receives the list of messages that is already received by the receiver side, and I think that is how it understands that the 3 and 4 are missing, like n plus 3 and n plus 4 are missing, and that's
So
when it
what you're
returns.
saying is this guy is sending
Negative acknowledgement.
status PDU. So
Yes.
what it contains, this status PDU,
list of packets that is already successfully
So
received.
it says n, I got n successfully, I received n plus 1 successfully, I received n plus 2 successfully,
And
but I
then
didn't
blank.
get, yeah, n plus 3, no, n plus 4, no, right?
Okay, okay.
So since this is like a positive acknowledgement, that's the reason why you see the color coding has changed from red to green for these 3 packets. So compared to
Yes.
t equal to 3, t equal to 4, we have marked these 3 packets in green. Now because now the transmitter comes to know that receiver has successfully received these packets. That way we can advance the window at the transmitter side. That way you can see that window has been advanced. And also the sender comes to know that n plus 3 and n plus 4 are lost. So that is what I'm showing it here. T assembly timer expires and the receiver is sending a status report informing the loss of n plus 3 and n plus 4 along with successful reception of n plus 1 and n plus 2. So in this case, yes, they have advanced their windows and the sender has retransmitted n plus 3 and n plus 4. And in this case, the receiver also is able to successfully receive the thing. And this example, what I'm also showing you at t equal to 5 is the sender knows that this is the last packet. So whenever the sender knows that certain thing is the last packet, it polls the receiver for a status report. Okay. So it is retransmitting 3 and 4 and seeking the status report from the sender. In this case, okay, I think, yeah, sorry, animation is over. Yeah. So yes, it is t equal to 6 is like something like transmitter has received the polling status report or the status PDU from the receiver, and accordingly both of them updated their windows and marked everything as successfully received. Does that make sense? What is happening here? So,
Sir, I have a query. Sir, does this mean that every time the reassembly timer expires, the receiver will voluntarily send out a status PDU to the transmitter?
see, whenever the timer is expiring means the receiver has to explicitly seek retransmission from the sender. So the way receiver can seek is by sending a status report.
Yeah, okay. Yeah. So that doesn't, so in 2 scenarios, the receiver will send a status PDU. One is when it gets an explicit request from the transmitter.
Yeah.
And the other one is when the reassembly timer expires.
Exactly. So yeah, you are right. This is a case where you can expect. Yeah. So this is the case. Here it is sending polling. Okay. And as a and whereas here it is the expiry. So these are the 2 cases where we get feedback from the receiver to the sender. Yeah.
Okay, sir. Thank you.
And things have become quite simpler in 5G compared to 4G because, as I was mentioning here, even look at a time t equal to 4. At t equal to 4, if you look at the illustration, so n plus 5 has been received successfully even before n plus 3 and 4. So this n plus 5 is immediately given to the PDCP layer because we are not doing any reordering or guaranteeing any in-sequence delivery. But in 4G, in LTE, we also do this in-sequence delivery at the RLC layer. So that way this n plus 5 is kept on hold till you receive n plus 3 and n plus 4. And after that, you'll be sending these 3 as a bunch to the PDCP layer. So that thing has been removed in 5G. One of the reasons why they are removed is to remove the requirement of having large buffers at the RLC layer. Whenever you have to do the reattering means you need to have large buffers, and with the 5G, with more and more channel bandwidth, you may end up really getting lots of packets in out of order with all these stop and wait processes and other thing that I'm showing here. So you may have to end up storing a lot of things in out of order and keeping track of that. So because things are getting complex, they simplified compared to 4G in 5G by removing in-sequence delivery from RLC layer and sending the packet that are successfully received immediately to the PDCP layer. And if the application demands certain kind of in-sequence delivery, let PDCP can handle it. If not, anyway, we can use a TCP or quick kind of protocol that kind of guarantee in-sequence delivery to the applications that we have. So that is the kind of philosophy that they followed. That way, this example that you see is a simplified version of what is there already in 4G. Okay, so let me move on to discuss about something called communication channel. So I have shown this particular architecture earlier as well. So far we looked at these three layers: SDAP, PDCP, and RLC. Now we are venturing into MAC. Before I start talking about MAC layer, let's look at the channels. You see there are three main channels apart from the flows, bearers, and RLC channels. So one is the logical channel. The second one is the transport channel. And the third one, which is not visible, which is the one that is handled by the physical layer, is the physical channel. So these are the main channel that we have in 5G. Even in 4G, we have the same three channels. If you look at except HDAP layer, more or less what I'm describing here as part of the protocol stack is also applicable for 4G. That way you are learning both 4G and 5G simultaneously, because 5G is a kind of superset of 4G. So let me explain what are all these three channels and how they are related with each other and how they help in sending user data and signaling information. So as I was mentioning, we have three channels. The first one is called logical channel. So we define these channels based on the information that we carry inside these channels. So depending on whether they carry control information or user information, they are called as control channels or the traffic channels. As simple as that. If it is a signaling information, you call it as a control channel. And if it is user data, you call it as a traffic channel. Again, try to come back and see what these channels are. Come back and see what is happening here. I'm talking about, we have control traffic channels, and also we have control logic channels, and also we have traffic channel. So here you carry the user data, and anyway here you carry the signaling information. So far on the discussion that I'm showing, where I'm showing the sending of the packets and all, that is very generic sense. And very often we talk about the QoS flows and sending the data from the QoS flows to the bearers, etc. But in addition to that, we also have these RRC messages that also comes down. So where you bypass the PDCP RLC layer and you directly give the messages to the MAC layer. In that case, for RRC messages, you create control logical channels. If it is user data, you create traffic logical channels. That is the meaning of that, where the MAC layer takes these multiple logical channels together and multiplexes them, and also does the hybrid IRQ before it mapping the data to something called transport channel. Second one is the transport channel. It is defined by how and with what characteristics the information is transmitted over the radio interface. So it is very interesting. The first category, that is the logical channel, is defined based on whether it is a user data or it is a signaling data. Whereas the traffic channel is defined, transport channel is defined by how and with what characteristics the information is transmitted over the radio interface. So take an example. Let's say you want to send system information. An example of system information is what is the bandwidth of the cell. So this is the kind of information that every user should be aware of. When the base station is advertising this specific system information, even the cell edge user should be able to reliably receive the thing. So can you tell me somebody, when some information has to be received even in a reliable manner by cell edge user, what is the thing that you will be typically doing it to ensure that even the cell edge user will receive that data? Can you tell me, based on what you understood in this course, how you can improve the reliable data delivery even to the cell edge user?
Sir, use lower modulation schemes.
Yes, one is you can use the lower MCS. Yes. Anything else? Yeah, maybe you can also say use max TX power, right? Whichever is allowed by the regulatory. Okay, we can do that, isn't it?
Protocols that ensure reliable delivery.
Yeah, we can. Basically, what you are saying, Madhuri, is indirectly you are talking about employee ARQ if it is
Yes.
important. But if it is broadcast, we don't use ARQ. But again, if it is unicast data, you can use ARQ. Okay. And other way of achieving ARQ is duplication. Sorry, not other way of achieving ARQ. Other way of achieving reliability is duplication. If certain information has to be reached by everybody, what you do is send the same information multiple times so that somebody can receive at least one of the times, if not at all the times, because of the poor channel conditions. So that is what I mean by transport channel. So depending on the nature of data that you wanted to carry, you define different transport channels. They are defined by how this information is carried, whether the information is carried using lower MCS, using duplications, transmitted using maximum transmit power or not. All these are the things are automatically configured depending on the nature of the transport channel. The last one, at the end of the day, that is the real one, that is the physical channel. It is defined by the time frequency resource grid on the underlying frequency band that is used to carry the information over the radio interface. At the end of the day, all these logical channels have to map to the transport channels. These transport channels has to be internally mapped to the physical channel. Physical channel is the one, if I take a TDMA frame, inside we have slots, right? So at a high level, you can I have not discussed so far about how the frame structure in 5G looks like. That I will cover in the following class. But at the conceptual level, you can assume that physical channel is nothing but one of these slot. So what you do, you take transport channels and you map them to the physical channel. You can say, okay, time slot 0 is physical channel 1, time slot 1 is physical channel 2, time slot 3 is physical channel 3, something so on. So like that, you do the multiplexing of logical channel to transport channels, multiplexing of transport channel to the physical channel, and send it using the antennas over the air. How you define these physical channels? Each physical channel is defined by the timing. That's what I was mentioning, time slot 0, time slot 1, so on. And also the access protocol, how the users will use these physical channels. Especially in uplink, we have something called a random access channel, where whenever your handset wants to send something in uplink, where it has not got any resources to transmit in uplink, it has to contend for the channel using slotted aloha. So whatever the slotted aloha you have studied earlier has a role even in 5G. It is also there in 4G and previous cellular networks as well. We use it only in a controlled manner when the user doesn't have any resources and when you wanted to express his willingness to transmit in uplink. So that is the access protocol. And again, the data rate, as I was mentioning, it is related to the MCS that you want to use it. So you define for different kind of information, what is the MCA that you should be using to send the data. So at the high level, these are the relations between these three things. I will explain each of them a bit more detail in the following slides. Let's look at the logical channels. So MAC layer is the one which offers the logical channels to the RLC layer. So we have two broad classes of the logical channels. One is control channel and another one is the traffic channel. So don't worry too much about these acronyms, but the notation, once you start paying attention, it looks somewhat easier to comprehend. So last two characters says that it is a channel. So the BC here stands for broadcast control. PC here stands for paging control. As you see, letter C we are using in general for control. This is for control, this is for channel, and we differentiate based on the first or the second letter. Where in this case, the first letter is saying it is a common control channel. Okay, let's look at what broadcast control channel does. It carries the system information like what is the cell bandwidth, something like that. The paging control, whenever you are getting incoming messages or incoming calls, that information is carried inside the paging control channel. Second one. The common control channel is the one that carry the information that is meant for all the users. Okay. So basically we establish signaling radio bearer 0. So along with the data radio bearers, each user is also given multiple signaling radio bearers to carry varieties of the signaling information with a different reliability and different data rates. Where for SRB0 we use the common control channel, and for SRB1 to 3 we use the dedicated control channel. That means these signaling messages are something that are specific to UV, per UV specific. Whereas these are the one common for all. So these are all the for control. And when you look at the traffic channel, we have one main channel that is called dedicated traffic channel, which carries the user data. Then when it comes to the transport channels, to which you multiplex the logical channels, we have again downlink channels and also uplink channels. What happens is in each scheduling interval, like in LTE, the scheduling interval was 1 millisecond, whereas in 5G, we have the scheduling interval of 100 microseconds, 250 microseconds, 125 microseconds. That means base station can decide who should be served for the next 155 microseconds regularly. Every 125 microsecond, it can decide which set of users it want to serve. So that's the reason why we say the cellular networks, especially the 5G, is applicable for even for mission critical applications, because we can able to do the scheduling even at the granulates of hundreds of microseconds, not at the milliseconds. Okay. And if you look at the channel names, they look very similar to what I described, because at the end of the day, what we have in reality is the physical channels. All other things are kind of different names in terms of what they carry and how they should be carried. And if you look at downlink channels, we have again the broadcast channel. It has something called fixed transport format. When I say fixed transport format, it talks about what should be the size of the transport block and what should be the MCAs that should be used and what kind of antenna mapping that you have to do. So these are the things that are defined or vary from one transport format to the other transport format. Whenever the scheduler decides to serve certain user, it has to decide how many resources to be allocated to the user and what MCs to be set for that particular user, and what antennas there is a MIMO kind of configuration that is out there. So that is the one. Whereas in the case of broadcast channel, the transport format is fixed. As I was mentioning, this is the one that everybody should listen. A part of the BCCH, which is called master information block, which contains the cell bandwidth information, is carried inside broadcast channel. And we have something called a downlink shared channel. So this is the most commonly used name or term, downlink shared channel. As the name says, this is the one that is shared. Anybody having any issues in joining or? Any issues anyone facing? Okay. And yeah, downlink shared channel is the main channel that you have in the downlink, which carries the data of many different logical channels. Like it carries the user data, signaling messages, the rest of the broadcast control channel information like system information blocks are carried inside. I will come back if at all we have time in the course. What are all these MIBs and SIBs? Basically, these are the things that are important when your handset wants to connect with a base station. When you switch on, sometimes your handset is in the coverage of more than one base station. So which base station to connect and all that is important. And to take that particular decision making, this information is important. What is carried inside MIBs and SIBs. And SIBs are one that are even very interesting. For example, SIBs carries information about what are all other base stations that are available, what are the small cells that are available, whether we have the dual connectivity feature enabled. All that information can be carried inside SIBs. Then we have the paging channel, which is used to carry the paging control channel information. In the uplink, we have similarly the key channel, that is uplink shared channel, which is used to multiplex multiple logical channels. As I was mentioning, we have something called RATCH, where we let the user to contend with each other using slotted hello protocol whenever they want to send some data in uplink, where they don't have any resources allocated for them to transmit in uplink. So finally, we have these physical channels. Again, we have downlink physical channels and uplink physical channels. And look at the names. At the end of the day, yes, these are the ones that really carry the data. We have the prefix B comes here. P here stands for, it is the physical channel, as you see, P. Otherwise, the rest of the things similar to what you discussed in the case of transport channels and the logical channels. Where you have something called PDCCH, that is physical downlink control channel, which carries control information like which are all the users that are going to be served in the current scheduling interval, and what user can transmit in uplink in the current scheduling interval, and a slot format indicator. So as I was mentioning, in LTE we can, in 5G we can do scheduling at a different time granularity. For that, they have defined different slot and mini slot kind of structures. So that information is carried inside PDCCH. Then we have the physical downlink shared channel, which carries the user data and also the paging information. So both are carried inside the same physical downlink shared channel. Similarly, we have the uplink channels, PUCCH. It carries the uplink control information like hybrid ARQ acknowledgements, the scheduling requests that are coming from the users, the channel state information where the SNR information or SNR information that base station wants from the user will be conveyed from the handset to the base stations using physical uplink control channel. Physical uplink shared channel is the one that carries the user data in uplink along with the MAC level control information. We have the patch, which is basically the RAT channel to which it is mapped to. So you use content for the resources using this particular physical channel. So in summary, this slide should be able to easy for you to digest. Basically doing the mapping of all these three different channels in a hierarchical fashion. Let's look at the thing and appreciate how they are related with each other. The logical channels are the one that MAC layer is giving to the RLC layer, and where the MAC layer takes the data from different logical channels and multiplexing them onto the transport channel. And the physical layer takes the transport channels and maps them to the physical channels, which are nothing but time frequency resource elements on the underlying frequency channel that is used to configure the base station. So look at here, the downlink shared channel I was mentioning, it is the key channel that you have in the downlink because it is getting mapped by broadcast control channel, common control channel, dedicated control channel, dedicated traffic channel. All the data from these four logical channels are multiplexed into one downlink shared channel. If you look at broadcast control channel, a part of that is directly mapped to a separate broadcast channel, which is in turn mapped to the dedicated physical broadcast channel. When it comes to the paging channel and the downlink shared channels, they are again mapped into the same physical downlink shared channel. And we have something that is not related to logical channels. If you look at all these things, these are related to the logical channels, but the MAC layer itself adds its own control elements. So it is the slot format indicator, and this is the downlink control information, which is basically used to carry the in-band control information. That means when you have the MAC layer at G node V and the MAC layer at UV, when they want to talk with each other, the signaling messages are carried inside this particular PDCCH, and the corresponding one in uplink is the physical uplink control channel, where they carry the DCI and this carries UCI, uplink control information. So you'll see the uplink part here. Again, we have the mapping of 3 different logical channels into the downlink shared channel. And when you look at the RACH, it is there operating at the MAC layer alone. So for that reason, you can see RACH appearing only here. There is no corresponding logical channel here. It has its own physical RACH channel that is defined. Then you have physical uplink shared channel to carry the user data in uplink, including the control information that you see. This is like a control. This is also a dedicated control, whereas this is a common control. Then you look at the physical uplink shared channel. A part of the UCA, that is uplink control information, is sent over a dedicated physical uplink control channel, whereas the rest of them, which is not so important or that is not so critical, can be sent with a different attributes or different characteristics using physical uplink shared channel. You can see it here. There are 2 choices to send the control information. I can use PUCCH or I can use PUSCH. So both are defined, and depending on the scenario, one can use one of them to achieve the kind of guarantees that are required. Okay, so I think we have another 10 minutes. Maybe I will try to introduce what the MAC layer does using these channels. Okay. So, the MAC layer is the one that does the scheduling of the user traffic in downlink and uplink. It basically does the mapping between the logical channels and the transport channels by organizing the data that is coming from transport channels into something called transport block. Okay. It also does the priority handling between the users by means of dynamic scheduling. So depending on the QoS requirements of the various barriers that are set up, it can able to decide who should be given more priority over other. It is all defined in terms of the logical channels. It also gives the information about uplink scheduling and also the downlink scheduling. So I will talk more on this after I define what is this frame structure in 5G. You'll understand, but at the high level, you can assume that it is the MAC layer which does all these things using something called MAC scheduler. It also does the hybrid ARQ, as I was mentioning when I was discussing even the RLC mode, where unlike RLC layer which does only segmentation, no padding, the MAC layer does the padding if there is anything left out. And we have only a single MAC entity, unlike if you look at SDAP entity, PDCP entity, RLC entity, we have only one instance of the MAC entity that is defined or needed at the base station. And even if there are one base station, G node B, that is serving multiple cells, cell 1 and cell 2, as part of something called a carrier aggregation. So we can manage these multiple cells using single base station with a single joint MAC scheduler. Okay, so we'll discuss some of these issues, especially some things related to the numerologies when I'm talking about the frame structure in 5G. So let's look at from the user point of view how the MAC layer looks like. So now we should be able to understand what these all channels are about. Look at what user is doing. So we have the RLC layer above, and we have the physical layer below, and this is the MAC layer. So it is taking the logical channels of various kinds in downlink and uplink, where it is doing something called logical channel prioritization. So we can have, like if you look at here, I have 3 different categories of logical channels: dedicated traffic channel, dedicated control channel, and common control channel. So as you see, very often in most of the networks, we give more importance to the signaling information, because if the signaling information is not delivered properly, network may start even misbehaving or may not even available to carry the user traffic. That's the reason why they are given more preference or importance. So that can be achieved using something called logical channel prioritization by giving high priority to these control information. Then we do the multiplexing, where you take uh, data of these multiple logical channels. Let's assume that we have limited amount of channel resources and it cannot send data belonging to all the logical channels. Then it will take the high priority logical channels and multiplexes them and send them over uplink shared channel by using the hybrid RQ, where it establishes the stop and wait protocol. And as I was mentioning, the user equipment also does the RATCH procedure whenever it doesn't have any resources available, where it has to indicate its willingness to transmit an uplink by doing slotted aloha in the RATCH process. So in the downlink, that means user equipment also receives the data from the base station. In that case, the downlink shared channel from the base station, from the G node B, comes into the picture. So where it is getting the data over the downlink shared channel from the base station, and yeah, it is basically terminating at the hybrid RQ, where it can be doing multiple retransmissions if required. Then it can be sending it to demultiplexer if it is related to the multiple logical channels, and if the data is related to the some of the broadcast channel where I was talking about SIBs, that data is directly sent to the BCCH channel. And the rest of the information like MIB information will go directly to the BCCH, and the paging information will directly go to the PCCH. And one important thing is when your handset is getting data in downlink from the base station, whenever you successfully receive the data and after that you do the demultiplexing, you also may want to give the acknowledgements or you may want to give NAC. So ACK and ACK, which are part of the hybrid RQ process, will be sent as control elements. Again, the control elements also get added as you do the multiplexing. If you look, okay, maybe I think I have a slide in the following that explains this part. Let me talk about how the header looks like in 5G. So I was mentioning as part of that data flow in the downlink, I was showing we have something called distributed header, where we have different subheaders for each of the MAC SDUs, which are kind of added immediately before the MAC SDU. So if you look at, in this case, I'm having 3 SDUs, N, N plus 1, and N plus 2. Each of them is having its own subheader. This is a subheader. And the second one has its own subheader, and the third one has its own subheader. And when you have the MAC control elements, they are also added as separate MAC SDUs with their own dedicated header. And if you look at any of the subheader, and open inside. These are the kind of fields that you see. One is reserved field, and this reserved field is the one that is used for carrying the MAC control elements. That means by using different reserved field values, we can able to carry different kind of MAC control elements. For example, in the uplink, what user equipment will be doing is, it will be sending something called buffer status report. How much data is waiting in the queues, that information is sent by your handset to the base station as part of the buffer status report control element. Similarly, it sends something called power headroom. Basically, your handset is telling its battery level to the base station. So that is sent as part of another control element. So for that, we use the reserved fields to define different MAC control elements. Then we have the logical channel identifier. We have 6 bits. And if you look at the MAC layer takes the logical channels and multiplexes them onto the transport channel, where each logical channel comes with its own identifier. We can have 2 power 6 different logical channels defined here. Then we have this SDU length, where we can have either 8 bits or 16 bits. Whether it's 8 or 16 is controlled by this flag. Okay. Maybe I'll show you quickly how the MAC header looks like in 4G. So look at this illustration here. Unlike the previous case where you see the subheaders are kind of distributed and kept adjacent to each RLC PDU, in this case you see all the subheaders are grouped together and kept at the beginning of the MAC PDU. And also we have the different control elements that are coming. So this structure is followed in 4G for both the downlink and uplink, where we have the aggregation of the subheaders appearing at the beginning of the MAC PDU. Then we have the MAC control elements, and finally we have the RLC PDUs or MAC SDUs with padding if needed. So compared to this aggregated subheaders, what we have in 5G is the distributed MAC headers, where subheader is placed before its respective SDU. This is done to achieve something called a low latency operation. As soon as at the receiver side, you receive a packet, you also comes to get to its corresponding header as well. That way the processing can be faster. That is at the receiver point of view. But even if you look at the sender point of view, that means when you are sending the data by packing multiple MAC SDUs together, which belongs to different logical channels, we can do something called a pre-processing of these things even before you are knowing what is the scheduling decision. So very often what happens is the scheduler informs what is the transport block size, and depending on the transport block size, we have to look at RLC buffers of different logical entities, and you have to get certain amount of the MAC SDUs to pack together to create the transport block. This process can be done irrespective of what the scheduler decides about the size of the transport block, where you can try to add this header a priori without even knowing the scheduling decision. That is because we are distributing the header. Where the headers are localized, you take each SDU, you simply adding whether it is a reserved field or whether it's 8-bit or 16-bit or what is the logical. As you see, the subheader that we are adding to each SDU has nothing to do with the scheduling decision. Scheduling decision only influences the size of the whole thing. The scheduler decision says that I cannot send the whole thing. One has to be only sending this. Then only you'll be sending this, and if needed, you kind of take a part of that and do the padding if needed. So that's how we can do the speed up in the processing without waiting for the MAC scheduling decision. This was not possible in 4G because all the headers are appearing. That means you have to know how many you are packing together. That means you have to know what is the transport block size in advance. That means you have to wait till the scheduler decides which user should be served with what MCS and what transfer power and other things. Okay, maybe I'll stop it here. I think already we are at 4 o'clock. And if anyone have any queries, I can spend some time to answer them. Otherwise, those who are having other classes, please carry on.
Sir, I have a query.
Mm.
Sir, the size of the packet that would be sent out is decided by the MAC scheduler, right? How much amount of data can be sent in a particular slot.
Yes, yes.
So then, how does the RLC module decide on the segmentation size, sir? How does it know, like, whether it must segment this or not, or how?
Okay, okay. I think,
That
Rajita, that is an interesting query that you asked. If you recall, I was mentioning also in the previous class, uh, RLC buffers PDCP packets, right?
oh,
And MAC layer,
it takes from that buffer, right?
yeah, layer takes from RLC buffer by adding RLC header. Actually, RLC header is already available, and of
Already
course the
added.
MAC header. So that way you can assume that it's more like a cross layer where RLC and MAC work very closely with each other.
Oh, yes, it should.
Yeah.
And the segment size should always be less than the max size that is possible.
Yes, yes. So the point I was trying to convey here is we need not to know in advance what is the MAC PDO to construct the MAC transport block. What I'm saying is you can able to readily, okay, maybe I'll come back to the 5G. So you can able to get these headers generated in advance, right? You can get these headers generated in advance. And as soon as you know the scheduling decision, you can start adding depending on what control elements that you wanted to add and quickly send it the thing. So that was not the possible in 5G, sorry, in 4G, because in 4G, you need to know what is the size. Then accordingly, you have to decide how many subheaders that should be part of that. That is the main difference that out there. And one other difference between 4G and 5G is the control elements appear at the beginning in uplink and downlink. Whereas in 5G, what I'm showing here is uplink, where the control elements are at the end. Whereas when it takes to the downlink, the control elements appear at the beginning and followed by the MAC SDUs. And the reason why the control elements appear at the front is ideally you expect them to be at the front because control information is more important. But for the uplink, they have decided that, especially when you're talking about low latency application, sometimes even you want to carry very low latency for the application traffic as well. To give the preference to the application traffic, the MAC control elements are pushed at the back and MAC SDUs are kept at the beginning so that the receiver can start processing the application data first and then worry about the signaling part. It is a kind of a design choice they had, slightly different from what was there in 4G.
Okay, sir. So the RLC packet size should always be less than the transport block, right?
Tell me again, Ranjita.
The RLC PDU should be less than the transport block. Should always be less than that. because from the buffer, the MAC layer will take the RLC PDU. So the header is also already appended and kept.
Yes, when I say PDU, already header is already there.
Yeah,
Yes.
so RLC header is already
The
appended.
header
So
plus
the RLC header plus the RLC SDU should be always less than the maximum transport block, right,
yes,
sir?
you are right. And yes, you are right. But very often what happens is the amount of transport block size is quite humongous.
Okay, okay.
So it's not that one packet. It could be you can able to send even 10 MB or 20 MB or even 50 MB data in one transport block.
Okay, sir, are these also configurable? These
It all depends on the channel bandwidth, right? At the end of the day, I will talk about in a separate class what is the frame structure and depending on MCS, how much amount of that data that can be carried in the. So those calculations we'll do. Then we'll appreciate. Yeah, it's all depends on the channel bandwidth.
okay, okay, sir. Yeah, thank you.
So then we'll be having these PDUs, but only after packing as many number of RLC PDUs, we'll be now looking at padding to match the transport block size given by the MAC scheduling algorithm. That's what. Yeah. So
So,
any other queries?
yes, sir. So please correct me if I'm wrong. Like in the IP, the internet, we basically fragment the thing, like the packets at the TCP, so that we based on the MAC, the
MCS. Yeah, yeah,
yeah,
MCS.
yeah,
MSS.
MSS. Yes,
MSS.
sir.
Yeah, right.
Yeah. So here also, if there was some way that we could provide the transport layer with the interval, so we can avoid fragmenting so many times, right? Only once can it be done? Like, is it a possibility?
See, whatever that you said also happens even here in the cellular network. MSS, the maximum segment size, that also can play in the end-to-end. But what we are talking is not the end-to-end. We are talking about in the radio access network between the handset and the base station.
Okay, so you're saying that there is need for internally also, like in.
Yeah, yeah. The reason why we are doing this fragmentation is, uh, see, we don't know how many channel resources are allocated to a given user or a given QoS flow. So depending on how much is given by the scheduling algorithm, we have to appropriately pack those much. Like if you come back, so look at this example. The MAC layer is the one that is multiplexing data that is belonging to dedicated traffic channel, dedicated control channel, common control channel. So first it looks at the relative priorities of these different channels and decides to take data of some of those channels. Where if you recall, I was showing that one PDCP can be configured with 4 RLC entities. What is nothing but RLC entity? Logical channels. So like that, you take the data coming from the PDCP layer and put into different logical channels. So in the case of user traffic, the logical channels are nothing but the dedicated traffic channels that are out there. So like that, you have the data. Some is the system data, some is the user data. Then you look at the relative priorities and decide to take data of some of them. And you want to multiplex them. But how much to multiplex is the one that is based on the scheduling ratio. That is a transport block size. Because here we are talking about wireless medium where channel conditions vary quite widely, and because of that you have to keep changing the modulation and coding schemes. And even there are multiple users. The base station wanted to serve various users and guarantee their QoS. So amount of data that you wanted to take out from given logical channel can be quite varying it. So it can dynamically decide how much to empty from each of the RLC buffers which belongs to different logical channels. That's the reason why, yes, there has to be a segmentation. We don't call segmentation as such. Basically, we have to take the data at a byte stream level. That's exactly what even the TCP does. So depending on how many bytes that system is allowed to transmit here, you take that much amount of the data and add the corresponding header and send it as quick as possible. That way, point I was trying to convey is, yeah, this kind of fragmentation is inevitable because we are not giving guaranteed resources. But again, when you're talking about the QoS flows and admitting the flows with the certain guarantees, logically we are creating the resources and guaranteeing it. But to ensuring that that QoS is indeed guaranteed, we have to do all kind of tricks at the bottom, where you have to change the things and we have to print the resources from some of the channels and give priority to other one, so that even in the case of congestion, for high priority one, they feel as if they are having immunity against all these kind of losses and issues.
Yes, sir. Thank you. Got it.
Sir, in 5G, with respect to QoS, sir, we are ensuring or guaranteeing QoS only from the user equipment to the UPF, right, sir?
That's it. Yes, you are right.
Core network is still the best effort IP QoS only, no? Or else we may have to do the DipServ related configurations.
Yes, yes. Operators can guarantee which are the things that are under their control. That way, from UPF to the user equipment, they give these kind of QoS guarantees. And when there's internet traffic that is coming, as I was mentioning, you can use the DSCP field to be able to identify the nature of the traffic. And if they want to honor these DSCP values, they can appropriately create the QoS flows and give the service differentiation. But otherwise, they can map everything into a default bearer, and let's leave it to the applications to do something smartly there to be able to mask all these issues.
Okay, sir. Yeah. Thank you.